All right, so the purpose of today's lecture is to try to give you some idea of what to expect on this next exam. I also have a last year's exam as part of this. So, and so you can have a look at that as well and get an idea of the kinds of things that we're going to cover. This is for the second exam, and so it's not going to be as heavily focused on the same material that we had in the first exam, but there are certainly things that don't go away. So first off, think of Lecture 4. At this point, I'm assuming you understand Lecture 4 perfectly. So if you don't, you have to go back and look at that again, because those issues don't go away. And we also have other things that govern why we care about the processing of biomaterials, like flaw size sensitivity, grain growth, which we may review again, and capillary forces, all of which operate in MIM as well as they do in CIM. And in some cases, they are more important in MIM, like grain growth especially, than they are in CIM. We're not going to talk about processes from 1 through 8, so I won't go over the details of that. All right, but again, Lecture 4, you should still be familiar with. And some of the smaller fixture concepts are abstracts and so forth from Lectures 9 through 17. So as you should have already guessed, there'll be more abstracts on this test. And if you look at the sample exam from last year they've given you, you've seen that was followed through on. And just to reiterate, equations, you read and understand, but don't memorize them, please. Make sure that you know that gamma may not be always the same thing, all right? From equation to equation. I didn't write the equations. I can't control the fact that they repeat themselves when it comes to Greek letters. But, in the context of the equation itself, you should know what gamma means as opposed to gamma in some other equation, which governs an entirely different process or property. All right, and certainly, the rush to nano for everything, when are they good and when are they bad? All right, so they're introduced for good reasons, but they can cause complications, certainly. That rush to make everything smaller means that there are issues with the process sensitivity that are caused by the presence of those small particles. All right, and so that's something that can be an issue going forward. And then something new that relates to the metal injection molding side end of things is oxidation. All right, we didn't worry about this with ceramics, but metals we absolutely do. And we know that oxidation is helpful to us in terms of performance of these alloys, and that if we didn't have oxidation, they might not be very useful materials to us because the oxide layer provides a kinetic barrier to oxidation. And that's something that is certainly part and parcel of what makes them useful for us. But we also have to deal with the fact that we want that oxide layer to go away as we heat this up. All right, so we have to do things involving the atmosphere to make sure that happens and make sure that the process of forming a microstructure proceeds as quickly as possible. Grain size control is an answer to the question of why is powder metallurgy important. All right, and so we know that powder metallurgy allows us to make small things, but it also allows us to control the grain size in a much more complete way than we can with casting. All right, and so this is a significant benefit to us, especially when we're talking about these biomedical alloys where you're trying to squeeze every last piece of performance out of these things you possibly can, and so you want to make the grain sizes as tiny as possible. So when you cast a large piece of metal, that is oftentimes not possible because that metal can stay hot for a while. And so we should know how we control these grain sizes and why it's important. And the one thing that still haunts us when it comes to metallurgy and injection molding is residual pore removal. First, again, why are they still there and how can we minimize them? How do we minimize the grain size to maximize the pore removal processes that we know are beneficial to us regardless of whether it's a metal or ceramic? Those things are still going to be important to us. And then we also have to deal with cooling issues. the why of cooling. So ceramics, of course, are more sensitive to this, but metals also have this issue. You can't just take a hunk of cobalt chrome and quench it to room temperature out of the furnace. It's not going to survive that. So these are other issues that are going to be common between these two areas. Any questions so far? All right. Liquid phase sintering. All right, and so one of the key things about the metals area are that we have these transient liquid phases. All right, controlled by, is there a question? Okay, these mysterious things in terms of superliquidous phases that show up in these particular alloy systems. So we have a liquid that will appear due to phase diagrams, and that liquid will be there and enable densification to occur, and then as you cool that alloy system back down, that liquid transforms back into a crystalline metal. All right, and so that's a very handy thing to have available to us in this context. So for certain metals, this is a handy goal for the process. So it's what they managed to achieve, and it works really well. Strength and its connection to processing. When can a lack of process control decrease the strength? All right, so we know that we have issues associated with the grain size, we have issues associated with porosity, and if we don't control the process, particularly heating, we can have problems that show up in that area. And then NDE and processing. So we talked about this a few times, but just keep in mind what NDE is, what it stands for, what its goal is, why do we care so much about it, what we'd like it to be able to do, which is more than it can currently do, but it is very important to us because of the potential for NDE to really benefit this area. All right, so why is powder metallurgy better than casting? So you should be able to sit down and think about it, come up with at least 5 reasons for that. So this is something that, again, differentiates MIM from the old style casting, which is why MIM is displacing casting in a lot of different areas. From the trivial to the substantial, casting is going away. For things like engine blocks, it's not going away. But other areas, it has definitely changed things substantially from the bad old days in the 1960s especially. All right, binders and MIM. So the beauty of this and a lot of other areas that CIM and MIM have almost the same binder systems in many cases. All right, and so the goals are the same. Trying to get perforation, trying to remove one, leaving space for the other to sequentially degrade after that. Those are the same kind of goals we have here, and they're also operative. The difference, I guess, that I should bring up is this, the concept of handoff as we go from being a solid made up of particles to a solid made up of grains. All right, that's a delicate transition, as I hope you know by now. And so that's part of where binders have to be much more precisely engineered in this context, so that they do what you need them to do when it needs to be done. All right, and so we know that metals can soak up carbon, and that's a good thing. All right, but it has to be done at the right time in the right place in order for this to successfully transit into being a useful solid. All right, injection molding. The details, flow test, which I think is on this exam I'm about to talk about. And that's, again, the concept of trying to make complex parts, complex shapes. We still have to think about how that can be assessed. And then the other aspect of this is the debinding revolution. So the before versus the after, the 1960s versus the 2020s. And so what we had to do and now what we can do, where we take what used to take days of time and thermal energy, now is a couple of hours of time and thermal energy. So it's a big benefit, especially for MIM. And then something that we didn't have to think about too much for ceramics, though, for metals is very important, is the sintering atmosphere. So with ceramics, with the exception of silicon nitride and silicon carbide, which we don't really care that much about in this class, you throw things into a furnace in air and you're good. All right, that was fine for the vast majority of oxides. Not so for metals. All right, and so we not only is it not air, it's also more than one atmosphere. We can have, starting out with a hydrogen-based atmosphere, not hydrogen 100%, but 4%, 5% hydrogen, and then switch over to argon or switch over to nitrogen, whatever works for us in terms of properties. All right, so it's a different situation, and it gets into this concept of Thanks for the musical introduction. The idea of the furnace as having chemistry, quote unquote. All right, so it's not anywhere near as simple as it was for ceramics, and this chemistry concept is what we use to try to introduce that idea and think about what happens when we have chemistry involved. There is a such thing as too much sintering, all right? So you should already have an idea of what that is, but in the context of metals, it's probably even more important with metals because, again, this huge need for grain size control and other aspects of compositional control, making phases that shouldn't be there, all right? So you can't just have it sit in the furnace forever. It's got a limited ability to be in there, and the temperatures involved are also going to be limited. And then the other aspect of this that is quite different from ceramics is particle morphologies. All right, so we talked about the difference between these wonderfully vacuum atomized powders that are just a modeler's dream in terms of their morphology, and the fact that sometimes that's not going to work. Sometimes we have to bring in some uglier particles to give the resulting compact some strength so it survives the transition into being a centered microstructure. So keep that in mind as well. Any questions so far? That's kind of the old stuff. All right. So micropowder injection molding, what is it? Why do we use it? It should be pretty straightforward. And then these solid freeform 3D printing, additive manufacturing. I was just talking about some guy who wants to set up a lab in 3D printing. What is this and how does it compare to other processes? So we know that, of course, making plastics by 3D printing or additive manufacturing is pretty straightforward. But in the context of making these complex biomedical alloys, it's a lot tougher. It's a lot more difficult to deal with. We still have issues associated with this MIM that relate to what happens with additive manufacturing, because we still have binders that need to be removed. All those things are going to be important to us, and we have to try to transform a collection of particles, because we're still dealing with particles even though they are printed, into a microstructure, which is not anywhere near as easy as it is for plastics. All right, and then plasma spraying. We know what the goal of plasma spraying is. We know what the ideal picture of plasma spraying is, but now, based on what I showed you and those videos and so forth, you should have some clear idea of the limitations of plasma spraying, and that it's not a ISO any type of process. It's a gradually adding some here and there sort of process. It's not like we form it all at once. And so because of that limitation, there are limitations in terms of the goodness of the coatings that we make. And we overcome that because we're not asking those coatings to have fantastic properties. What they sit on has to have fantastic properties, and the process of coating it shouldn't compromise those properties. And I showed you a lot of work in the area of hydroxyapatite, especially for good reasons. And there are a variety of other materials that are also plasma sprayed. And then last but not least, trabecular metals. Why do we like trabecular metals? Right, what makes them significant for us? And this has to do with a biological response and how that's important. So we get a trabecular metal that has a different modulus than the solid version of the same metal, certainly. Because its modulus is lower, but it still has good mechanical properties. It makes a better substitute for bone and helps minimize some of the stress shielding concerns. So I showed you those x-rays, a big hunk of titanium stuffed into a femur, and the consequences of that and as far as stress transfer is concerned. So you load one area and you unload the other area of the bone. That unloaded area gets weaker and weaker and weaker as time goes by, because that's what bone does. It takes away mineral content from areas of bone that are not stressed. All right, which is why the astronauts, I guess they have treadmills up there now, but they used to, they'd get out of the space capsule and they'd wander around like old men because their bones get thinner when you're up there for a very long time in the absence of gravity. All right. Anyway, so things are better now. And then, of course, the processing conditions, specific tricks that are used to make trabecular metals, which are pretty cool, but it shows you that we still have to worry about the process in this context. All right, any questions about all that? All right, so with that, we'll go to last year's test. Consider electron beam additive manufacturing versus regular MIM. And so we know that we have this really interesting process of electron beam manufacturing or laser-based manufacturing. They're similar in a lot of ways. You saw that movie, and how they managed to transform a bed of powder into a solid. And consider the considerable differences in the number of steps that occur for each of the techniques, and from a basic material science point of view, compare and contrast powder processing prior to shaping. All right, so as you saw for the EBM or the laser-based system, you have a loose powder and you transform that layer by layer. For MIM, you have a bunch of that powder in a solvent or ideally a molten plastic, and those are two very different circumstances that get you to the end goal. All right, so you should be able to contrast those. Debinding, what are the relative difficulties? And so we know what we have with MIM, and we should have some idea of what goes on with E-beam or laser-based manufacturing as well. All right, so it might be very clean, but there's still some needs for binding. Debinding in some cases, other cases maybe you don't have binders present at all. So you have to basically define those differences and make those clear. And then atmospheric requirements during acidification, how might they be different and why? Why would the atmosphere for one be different than the other? And this may have to do with removing binder, the rapidity of the process. We know that E-beam is really fast, right? So that's something that is going to make things different in this context. You're trying to densify these materials. But we know they're both metals, they oxidize, so we already know we have to avoid oxygen. But what else is different between these two different processes? Any questions about that? And then one of my favorite questions. So basically what I do is I say residual porosity following MIM debinding has serious consequences for the reliability of biomedical products. Using the templates below, and this is where you have to very closely pay attention to the fact that these scale bars are changing, start sketching things for me. So you've seen a ton of SEMs in this class, so you should be able to more or less approximate an SEM. And sketch the evolution of a bimodal powder assembly, initially consisting of 8 micron particles and 1 micron particles into a microstructure having the densities shown. Include the presence of a small amount of polymeric binder, such as polypropylene, which is the good stand-in for a lot of this, at the end of the debinding process. And so I'm asking you to sketch something following debinding, sketch something following neck formation, and then we make the jump to something that's 90% dense. All right, so you have to be able to sketch me some microstructures. So I've already told you that it's 8 microns in size, and this is 1 micron, so we know we have 1 micron particles in there, and we know we have 8 micron particles in there, which are much bigger than the 1 micron particles, something like that. Maybe that may not be good enough, actually. Anyway, but something that shows the fact that these are bimodal, and then as time goes by, those guys will get together with a green guy, and they will make necks between themselves and that neighboring particle. So you'd have to show me in a little bit neater than what I'm drawing you, the formation of necks in these systems, right? And then what happens in terms of porosity at 90%? Where is it likely to be? Notice again, I've jumped up to 100 microns. So you can give me a lot of information on this. You might assume some grain growth. All those kinds of things could happen. And then at 98%, where's the porosity there as we transit from stage 2 to stage 3 of sintering? Does that make sense? Hopefully it doesn't seem too daunting to draw microstructures like this. Right, again, the whole sketching thing really helps hammer home the intuitiveness of this. All right. Any questions about that? Yes?
Are you going to put the answers to this on Carmen?
I am.
And then are there going to be more tests to practice with?
Yeah, there's going to be 2 more tests, yes.
Okay, awesome.
Yeah.
Thank you.
Sure. All right, any other questions about that? All right, and so this is another good question. The development of gas atomized metallic powders is largely responsible for the widespread application of metal injection molding. So we have these beautiful, nice round spheres. However, as particle size either decreases or becomes non-spherical, for reasons we already discussed, friction at a powder mass increases. So, first question, name 3 disadvantages of decreasing particle size with regards to mixing. So, as we go from micro to nano, there are issues as the particles become smaller. And what are those issues? You should be able to give me anything involving agglomeration, debinding, sintering, grain size. There's a ton of different things, all derived from the fact that as we go to smaller particles, these problems can become worse than they already were. It shouldn't be too hard. Describe how decreasing particle size would influence the length of travel and the zigzag test shown below. So you guys need to know what this is, why we're doing it, why it's important, and then way down here when things stop, what would be the particle mechanism responsible? Sketch the structures that might exist at that choke point in this zigzag test. Oh, by the way, choke was today's Wordle. I don't know if it does Wordle or not, but I do, so that's why I remember it. Yeah, I blew it for you guys, sorry.
I already did it.
Okay. I usually do them in the morning. Now you can get it in one guess. Hey, I think you're a genius now. All right. Hopefully that seems pretty clear. Sorry, I guess I should have kept my mouth shut. You have no idea what I'm talking about. Okay.
I'm in a competition for Wordle that ended today, but I found the secret to know what word it is every day.
There's a secret?
There is a secret.
And what is that secret?
Defeats the purpose. It defeats the purpose if you know how to find a secret, but since I'm in a competition with everyone else who doesn't know what source code is, then it doesn't defeat the purpose for them, because now I just automatically win.
Oh, okay. Well, that sounds kind of boring.
It is for me. But I won, so I don't care.
Okay. All right. Any questions about this that don't have to do with puzzles? Okay. Kind of a puzzle, yes it is. All right, so the equation and plot below. So we've seen this twice now, both metals and ceramics. The anticipated linear shrinkage relating to the initial post-debound density to the final cinder density for 2 specific final densities, 95 and 100%. And so we have this relationship between the densities in the green and the cinder states and the linear shrinkage, which is there because we can measure it easily. And then we have this graph that shows a very important set of relationships: solids loading on the x-axis, sintering shrinkage on the y-axis, and then 2 end goals, 95 and 100% final density. All right, so we should be able to rationalize why, any point on this x-axis is not the same as any other point on this x-axis, all right? And we also should be able to understand the barriers to high shrinkage situations, the benefits to low shrinkage situations, and the disadvantages of very low shrinkage situations. As we move to these really high solids contents, that carries with it issues. Right? It's not just waving a magic wand and expecting all the problems to go away. So as delta L decreases, what happens to rho sub S? What is the significance of this trend? And then we have these 2 targets. Why do we have these 2 targets? Why do we worry about those? This kind of gets into the differences between metals and ceramics in terms of targets, and what's useful and what's not. And then practical complications associated with large amounts of sintering shrinkage, major complications with very small amounts of sintering shrinkage. You have to think about both ends of this. All right, so theoretically, you want to be at solids loading of 90%. Practically speaking, that's not going to be a good idea for most solids. And then what is the major benefit of a small amount of sintering shrinkage, and when might it be used? All right, so that could be something that relates to an application, for example, or how the, let's say, the profit margin associated with that application might justify certain types of behaviors. Any questions about this? All right, so these look really scary or pretty straightforward, or? Okay, kind of, sort of. All right, And then another graph, straight from your notes. For copper powder, the relationship between sintering and grain size is shown below. So for a typical biomedical MIM compositions, give 2 reasons why minimal grain sizes are desirable. So we should have, at this point, a really clear idea why we like small grains. It's the same for ceramics and metals. Any real differences? Probably not. Where possible, grain growth inhibitors are used. Provide a sketch showing how they function. So we do have grain growth inhibitors in metallurgical systems. We want to know how they keep the grains from growing, just as we want to know why having grains grow is really bad under some circumstances. Is there a question? No? Okay. And then draw a new line showing the expected effects of a grain growth inhibitor on grain size versus density. So starting with this graph, where's that new line going to be if we can slow down grain growth? We do know they start from the same point because initial stages aren't affected by that grain growth inhibitor, but then when do they diverge and why? What does that resulting line look like? And then finally, what is the logic of fast sintering or fast firing, and how does this process modification achieve its purpose? And so it's even easier for metals than it is for ceramics because they tolerate these fast sintering rates much more effectively than ceramics do because they are more conductive. All right, but why are we doing this? Why are we taking the trouble of fast sintering in the first place? What does it preserve for us that makes it worth doing? So you should have a pretty good idea of what the answer to that question is at this point. Any questions about that? Doesn't seem too bad. See looks of shock at this point. All right, and then statements from the papers. So I just pulled these statements out of the papers, and they should be things that are familiar to you at this point. Variations in the initial powder morphology change packing characteristics and therefore the diffusion of the sintering atmosphere through the compact. So we know that atmosphere is important, very important in terms of controlling chemistry. But we also know that these are microstructures, or the microstructures beginning to form, or already started to form. So in that context now, we have to get the sintering atmosphere all the way into the compact, and the chemistry of that atmosphere, the amount of hydrogen in it can change as a function of motion inside the compact because hydrogen gets consumed by the oxidation reduction process. This altered the formation, size, and type of the precipitate formed within material type and the levels of surface oxide reduction, which is just what I said. The extent of precipitate carbide eutectic formation was also dependent on sintering temperature, with the largest variations in density being obtained at sintering temperatures greater than 1250 degrees centigrade. All right, and so that should be something that you are familiar with. You know how atmosphere can affect carbon content, for example. And we know that's also thermally dependent as well. And so these things can be important, and it should make sense to you that if we have like a femoral head, the outside of that femoral head may end up with different carbide content than the inside of that femoral head. Very, very likely. You may not care that much. Most of the action is on the outside of the head, but we do know that these are complex structures. It's a web of porosity, and it's not a direct pathway. And then the next one, sintering atmosphere had varying effects on the powders. Vacuum sintering, which seems like it should fix things, led to high levels of chromium volatilization and decarburization. So it's not fixing things, it's making things worse. Again, chemistry at work here. Sintering in argon proved to be highly protective atmosphere, permitting large volumetric quantities of these various carbides to form. Okay. For statement 1, how could powder morphology affect both identification and chemistry-driven properties? Relate your explanation to specifics from that first statement. And then for 2, how does atmosphere affect both composition and mechanical properties? Relate your explanation to specifics from that statement. Okay, so do you have a handle on how to answer both of those questions? No, we don't have a handle? We do have a handle.
Like a medium. I have a medium handle on.
A medium. Okay. All right. right. Yeah, so it's not as straightforward as just atmosphere and a metal surface. When you make a three-dimensional object, you create gradients, and those gradients can influence properties as well as grain size, as well as composition. All right, but the main things here, we know that atmosphere is important. We know that throwing temperature and time at these microstructures is not always going to fix the problem. It can make the problem worse. All right, we know that the atmosphere, which initially helps us, can end up hurting us depending on how we utilize that atmosphere. All right, when is the test? What?
A week from next
A week from Wednesday. Okay, all right. So we're all on the same page there. Any questions? Everybody ready and ready to go? Looking forward to it?
Is this our last class with you?
It is your last class. We're going to teach more classes?
That's if you want to.
If I want to. Yeah, no. No comment. Put it that way. The wisest thing to say. All right. So.
Makes it sound like you don't like this.
No, it's not you at all. It's not you at all. It's other aspects of the department. Anyway, which I also shouldn't comment on. Okay.
That's relatable.
Okay. All right. So, yeah, I'll try to post the answers. Well, I need to post the test first, but then I'll post the answers on Monday of next week. All right. Okay. All right. We'll see you Wednesday next week then. So, hope you guys enjoyed the class. All right. And good luck on the test.
Thank you.
Oh, yeah. So the extra credit stuff. How does that look? Have you guys looked at it yet?
To be honest, I haven't.
Okay, all right. Just have a look at that. It shouldn't, my view is that it should take you at most 2 pages to type the answers, at most, and maybe another page for sketches or something like that, whatever you want to do there. But
Do you want it like typed?
yeah, I'm tired of trying to read your writing.
Yeah, your
All right.
handwriting sucks though.
It has since I was a kid.
Did you want us to email it to you, or did you want us to
They print it out.
print it out and send it to you?
Oh, you're not gonna be here.
I'll be here Friday.
I thought this was your last class.
We as well.
I'll be in my office. Yeah, you probably under my door. Or you can email it to me either way. I'm not going to die. No, you can email it to me, whatever, it's fine. Yeah.
But the sketches, we could draw, right?
You can draw, yeah. And I don't know how you want to put them, just take a picture or something.
Imagine not having that.
Dylan, are you gonna just do it in Word?
Well, he said type, so I didn't know that. If I had to draw things in Word, I would have been.
No, that's not worth it. Yeah, no.
Yeah, I would have just got those questions wrong.
Yeah.
Okay. I'm working on a research project and we're trying to 3D print something and we were looking for a coating. Do you have any ideas of like a hydrophobic coating that we could easily use for like a 3D printed thing like made of PLA?
And so the hydrophobic coating is going to do what? Protect it from
Yeah, from like the
moisture?
cells in the media and stuff, yeah.
So you want the cells to see a hydrophobic surface. The cells don't like hydrophobic surfaces.
Yeah.
Okay.
We don't want them to. Like
Okay.
we want it to be like protected from all that.
Yeah, so I would go with a PDMS resin. So it's these 2-part PDMS resins and mix them together, and then you just let it sit overnight and it forms polyvinyl siloxane,
Yeah.
and that would give you a hydrophobic surface. That's probably the most straightforward way.
Okay, we already use PDMS for like our other devices, but I think we're looking for more like a thin coating.
Yeah, so you just dilute
Yeah.
it down in solution and then
Yeah.
dip it in there and
Just
pull it
dip
out.
coating with PDMS, is that easy?
Well, yeah, but I wouldn't use pure PDMS.
Yeah.
Yeah, solution of the 2
Yeah.
components. Yeah, that should be that easy. Yeah.
Okay, awesome. Thank you so much. That
Sure.
saves us a lot of time.
Yeah. Good.
So I looked at my test, and I lost the most points on the sketch question. So, can we meet on Thursday to look at that question?
Sure. What's a good? I'll watch on you today. What's a good time on Thursday? Like in the afternoon, late afternoon?
Yeah, I have class at 11, but besides that, I'll be free.
It's like 4-ish maybe. Okay. All right, that'd be fine. Do you want me to send you a Zoom invite?
Yeah, that works. Or I'll be in the building. I don't know if you'll be in the building.
If you want to stop by, that works too. I don't have a preference.
You don't?
No.
Okay. Then yeah, can we do it in your office?
Okay, all right, that'll work. All right, see you then.
Thanks.
Sure.